Okay, we're ready for notes for 2E in the Math 4 course, and I'm going to start out with this. These are the kind of pictures that I would have on the board as you were walking in, and this was one of those that I intended to kind of challenge, would you do this or would you do that? And so I'll give you the answer when we get to the end of this. All right, 40 kilometers per hour or 15 meters per second. Which one would go faster? All right, today we are playing with composition of functions, which should be, again, a review of what you learned in Math 3. Although we will pick up a few new items along the way that I'm pretty sure you didn't discuss then. Now, right now we're just hitting the basics: add, subtract, multiply, divide. If I take these two and take that and add it to that, I really can't simplify it any further, so we're done with that one. When I take f of x, which is x squared, and I subtract g of x, again, I get something that is in simplified form. Now, when I say x squared times 4x, I'm going to wind up with 4x cubed. All right, the next set, we're doing more dividing and subtracting. This time we're going to have f of x on top, g of x on the bottom. Now there is an x in common. There's an x in both of them that can simplify, it can cancel out and leave us with that. Now in this case, we're doing that minus that, which I am okay with that. Some teachers may want it in proper descending order, x squared, then x to the 1. I would take it either way. And then the last one, we have the 4x, g of x on top, and the x squared on the bottom. Once again, I have an x that is in common to both of those that will cancel out and leave me with that. That's what those are going to look like, and that's just your basic operations. Now, when we get down to the composition of functions, this was something that would have been, I don't know, it depends on whether your teacher got there or not. But the idea is that when you are doing, whether it's in this order or in that order, they're basically saying the same thing. You worry about the guy to the right first, and when you are done with him, then you stick him into the guy on the left. And likewise, we're going to do h of 4 first, and then we're going to stick him into g when we're done. Now, let's do some color coding here. That's red. That's blue. And that's yellow. Okay. So we're going to start with g of x first of all. That's going to be square root of -1 plus 2 equals square root of 1, which is 1. And then we're going to take him and put him inside of f. So we have 2 times 1, which is plain old 2. And so that's going to be the end of that one. All right, next we are starting with h of x first. We're going to figure out what is h of 4. That's going to be 3 times 4 minus 5, which is 12 minus 5, which is 7. And then we're going to stick a 7 into g of x, which is blue. G of 7 is going to be 3 times 7 minus 5, which is 21 minus 5, which is 16. Now for h of h, it's like we run it through once, which is going to be -5. And then we run it through a second time. We take our new answer and we plug it in, which is going to give us 3 times -5 minus 5, which is -15 minus 5, which is -20. And I guess, well, I'll save that story in just a minute. We've got a few other examples here to work through. I think we had H as yellow, and G as blue, and F of X as red. So now instead of plugging numbers in, we're using X. And maybe the easiest way to describe it is this. I'm going to stick G inside of F. So I'm going to start with F. I'm going to leave a big hole where X is, because that's where we're going to stuff G. We're going to stuff G inside of F. And so instead of 2x squared, now it's 2 times this that is squared. Well, the square and the square root are going to cancel each other out, and we're going to be left with this. X plus 2 is still in parentheses, which distributes out to look like that. Now, for the second one, for E here, H goes on the outside, which means that we're going to have 3 times some sort of X minus 5. And we're going to stuff an F of X inside of that, like that. 3x minus 5 becomes 3 times this minus 5. We're going to stuff F of X inside of H. Well, by the time that we finish distributing, we get 6x squared minus 5, and we can't simplify any further. Now the F of X is where we're going to take the 2x squared and put a big gap where the x was, and we're going to stuff another 2x squared inside of it. So by the time we square everybody inside the parentheses, we have 4x to the fourth, and then we multiply by 2, and we get 8x to the fourth. Now, this one is going to be a longer conversation, because when we ask about the domain of each one, what technically is going on is when we start combining these, whether we're adding or dividing or doing one inside the other one, the domains have to overlap. I guess that's the best way to put it. Now, let's look for a second here at both of these. Now, if I do square root of x, the graph is going to look like that, and my domain is going to be from 0 all the way to positive infinity. But when I start looking at the square root of 3 minus x, well, that's really the square root of negative x plus 3. And we've had conversations about this before. The negative inside means that I'm going to flip it the other way. It's going to flip across the y-axis. It's going to flip left to right. But for some reason, the plus 3 in there does not mean that we're going to go left. I think it has to do with the negative inside the square root. The plus 3 actually means that we're going to go right. And of course, it's been flipped. The negative x means that we flipped it, but for some reason, the plus 3 comes over here, and that's a special case. But that means that my domain is going to start at negative infinity and go all the way up to 3. Now, the question is, where do they overlap? Now, sometimes I like to draw out a number line. And I got 0, and I got 3. And what's going to happen here is that the red guy is going to go like that. And the blue guy is going to go like that on the number line. And so when you ask where are they overlapping, they're overlapping from 0 to 3. And that is the domain of this guy. Now, by the time I put these together like that, and let's start playing around with the domain for a second. What if the domain was, what if the x value was -1? Well, it wouldn't go in the left one very well, would it? I can't have square root of -1. I can't have square root of negative anything. So anything below 0 is out. Meanwhile, this guy here, anytime that I go any bigger than 3, if I stick a 4 in there, I've got 3 minus 4 is -1. Now I got a square root of -1 again. So I can't have anything above 3. You know, at least with a 0, I get square root of 0, which is 0. With a 3, at least I get 3 minus 3, which is square root of 0. So I can live with those. I just can't go outside those boundaries. Now we're going to find that these numbers are going to come back to haunt us on the rest of these. So if I say square root of x goes on top, and the square root of 3 minus x goes on the bottom, well, it looks like I'm having the same kind of discussion I was here, with one small exception. What about this x underneath? If I stick a 3 there, what's going to happen? I'm going to say 3 minus 3 is 0, square root of 0 is 0, fine. And now I've got a 0 on the bottom of a fraction, and I can't do that. So what's going to happen here is that I can do that, but I can't go all the way up to 3. I'm going to have an open circle on the 3, as it were. Now, in this case, we are taking the g of x on the outside, and then we're putting the f of x on the inside. Now, this is going to change the game just a little bit, because I have the square root of x, I still can't go below 0. So my domain is still going to stop there. But on the positive end, we get into trouble when this whole value gets above 3. If I can say 3 minus 3, I get a 0, and I'm okay with that. I just can't have the square root of x go anywhere higher than 3. Well, the square root of 9 would be 3. So that means that the square root of 9, the square root of 9 is 3. That means that x cannot go any higher than 9. Now, can it be 9 itself? Square root of 9 is 3. 3 minus 3 is 0. Yeah, I can do that. But I have to be aware of what goes in my x value there, and make sure that I'm not creating square roots that I'm going to regret. And, there is not, if you're looking for some sort of system that whenever I see this, my answer looks like that, I really don't know that you're going to find one here. You really are going to have to stop and imagine, where and what we did in the very beginning, found the domain of one, found the domain of the other one, and looked at where they overlap. That's probably the best starting place you've got with this conversation. So, all right, this guy. This is one of those that either you get it or you don't. That sounds kind of crass, but there are some people that struggle to no end, and there are some people that it just clicks right away. Don't know what the difference is. I had to spell out the English like that because I realized that when I printed this out on paper, I didn't have red and blue. I had, black and almost black. So I had to describe f of x as the curve and g of x as the straight line. That's probably the easiest way to keep them straight. So if I have, again, I'm going to start with g of -3, and we're going to stuff that into f when we're done. So g of -3, when x is -3 on the straight line, I am right here. That is the point 3, 1. So when x is -3, y is 1. That's kind of the name of the game. Now, what's going to happen here is that I'm going to come down here and I'm going to take that 1 and I'm going to plug it into f and see what he turns out. Now, on the f curve, when x is 1, I am right there at 1, -1, which means that when x is 1, y is -1. Now, this kind of begs a story that goes back to my college days, and I'll try and keep this short. I had a professor who was very Greek. Elias Katsoulis was his name. And he was teaching Calculus 1, and he had a very thick accent. We could understand most of what was going on there. And after a few days of class, you started to kind of get used to the accent. But there was one word that we could never figure it out. And he would talk about machin, and we had no idea what machin was. And finally, about 2/3 of the way through the semester, it finally clicked with me what was going on. You see, I also found out along the way that he was a computer programming major. That was what his doctorate was supposed to be in. And computer programmers, when you talk about an equation that you stick in a number for x and it turns out, whatever answer for y, they don't call them equations. Computer programmers call them machines. Yeah, machin. That was machine in his very thick Greek accent. And it clicked the day that I saw him at the board, and he kept pointing at the equation and saying the machin, the machin. And that's when all of that came together. And I suddenly realized that, he's a computer programmer. He's looking at this like a machine. I stick an X in the slot. I turn the handle, and, Y comes spitting out. And what's happening here is that we're actually sticking the X in the G machine, and it spits out 1. And so we take that 1 and we put it in a second machine, the F machine, and it spits out -1. And so, this it's almost like a flow chart. And that's why I wrote this in that pattern, so that you could see visually what was going on. Now, ultimately, you're going to say that f of g of -3 is equal to -1. That's what the final answer is going to look like. But it took some stages to get there. So, all right, let's try that again. This time, f of, let's see now, f is the curve, and g of x is the straight line. And so we're starting with f of -1 first. And so f -1 is going to be right there. It's going to be at -1, 0. So f of -1 equals 0. And then we stick the 0 into the g function. What happens when x is 0 for g? Well, for g, x is 0 right there. That's 0, 1. And so that is our final answer. And that is the way that the game is played. And like I said, this is one of those that either it clicks or it doesn't click. Now, the way that this is set up, we're going to start with g first. So we're going to start with g of -1. X is -1 right there on g, which is -1, 0. And so that means that if x is -1, y is 0. And then we're going to plug it into the f function. and figure out where on this parabola is x0. It is right there at 0, 3. So that means that my final answer is 3. Now, I'll take a brief minute to work with this. Which was faster, 40 kilometers per hour or 15 meters per second? Now, I'm going to approach this like a science teacher would. If you're trying to convert units, then you are going to say that 60 seconds equal 1 minute. So you're going to have 15 times 60, which is 900 meters in 1 minute. Because technically speaking, the seconds cancel out. Now, we're to meters per minute. We need to get to hours. So we need to take this one step further. We're going to do this times 60 minutes in an hour. And again, you see that we're going to be able to cancel out the minutes. That's the game of the whole thing. That's the whole goal, is, for those to cancel out. And so by the time we finish multiplying here, 900 times 60 is going to be 54 with 3 zeros. So we are doing 54,000 meters in an hour. And so now we're at kilometers per hour and meters per hour. So all we have to do is change the meters into kilometers. So we're going to say 54,000 meters in 1 hour times, and then you're going to change from meters to kilometers. So you're going to have 1 kilometer for 1,000 meters. And this is going to cause the meters to cancel out. Yeah. And what I am left over with is 54,000 divided by 1,000 is 54 kilometers per hour. So going 15 meters a second would be a little faster than going 40 kilometers per hour. That's how you do that.